Henk Akmans here, Supply Network Dynamics Chapter 2, Part 4, Negative Feedback Loops. So, of the two fundamental kinds of feedback loops, the negative feedback loops are the ones that try to keep order in the house. This one doesn't really, but still it is negative feedback loop, which negative feedback loops mainly means that if in a loop you start off with something becoming bigger, a number of things happen, the next thing becomes bigger, smaller, whatever, but in the end the same thing becomes smaller. So this negative feedback loop says the more rabbits you have, the more they will die, the fewer rabbits there are left. I think it's quite easy to make this as well. So I have a number of rabbits, and there is a rabbit death, and it may be according to a certain constant factor. I would say that we have 20 rabbits initially, and let's say that there's a decay factor of I don't know how many would die, 25% perhaps, that's a lot, but still. And the trick is that you would then say in the rabbit deaths, that's the total number of rabbits times the decay factor, and that's what we have that will die. I then make a graph around here, put both of them in there, and this is what you should see. The rabbits die, and there is a decline in the number of rabbits dying as well. Mind you, don't be fooled by the scale. Actually, these scales are different. You can see that better up here. So the absolute number of rabbits decays, the absolute and the number of rabbits dying per period also decays. The implicit notion is that it ends up somewhere towards 0. So that's the I think version of it. The calculus version of it looks a lot more like this. We have the value of the population at times t is equal to the initial population here, 20, times some kind of power of e. And as t becomes bigger, then of course this becomes smaller, and if this becomes smaller, then the whole thing becomes smaller. That's exponential decay with a proportional death rate, an outflow rate if you like, proportional to the total population. Don't be scared by the mathematics. I include them here simply for those of you who still know a little bit of calculus and have known exponential functions, and are pleased to see that there is still some rigor behind this fluffy simulation stuff. Those of you who have long forgotten it or never got it, be glad, because you can do all this cool stuff now with a very nice tool like I think. But for those of you who are mathematically inclined, just a little small mathematically aside, why e to the power of minus t? Well, we have this notion that the flow at any moment in time is equal to a certain proportion minus g, and g is then the combination of the in and the outflow of the stock. So you could say that the rate of change in the stock is equal to minus g times dt. If you then integrate both sides, then this side becomes the integral of ds divided by s. This then becomes the integral of minus g dt. And this, the ds divided by s, is just happens to be the predefined derivative of the natural log of s. Here you have to bear in mind that This is then minus e times t. You integrate it with the constant standard integration rules. Now how do we end up with S0? Well, at times S0, then the stock, this is this is 0 because t is 0, so at times 0 the stock of the 0 is only c. So s is 0, s at stock 0 times the power of e, because if you take from both sides the power of e of the natural log n of g, you get the power of the e to the power of a natural log, then becomes simply the stock. And here you've got e minus gt times the stock at time 0. So, for those of you who are so inclined, don't worry, I won't ask it at the exam. That's implicit feedback that we had so far, but in the vast majority of cases there is an explicit goal in the equation. So almost everything we do, your body and my body, is full of negative regulating feedback. The economy is full of regulating feedback. Nature is full of regulating feedback. The general notion is that you have a desired state of the system and a current state of the system. There's discrepancy between the two, and the bigger the discrepancy, the bigger the correction over a certain adjustment time. And this equation you will see in the 9 sims that we have over the coming weeks and months, 90 times or so. So you better understand how it works. So the inflow rate is the desired stock at this desired level minus the current level over some adjustment time. So if we have an initial population and a sort of target population, as you would have in this model, then the story changes, because that means that you work towards a certain goal. And when you are there at the goal, then you don't change a lot anymore. I won't reproduce this in I think anymore, because I think you can do that quite nicely yourself, but I suppose you see the point. A target, so mind especially the rate equation here, the population change is the target of the population times the minus the current population over some kind of a change delay. Again, there is mathematics behind this, which is again especially for those who find this interesting. The calculation is slightly more complex. What is interesting here is what you see in the net result. The flow at any moment in time is equal to the desired stock minus the stock that is today over some adjustment time. So then you get this formula in the end. The stock is equal at any moment of time is equal to the desired stock plus the gap between the initial stock and desired stock over some adjustment period. So if initially you have 100 and the desired stock is 20, then it's the gap of 100 minus 20, the 80 that you start off with, and that gap becomes smaller over time, because as t grows, then this becomes smaller and this becomes even more small. I'll get to delays in just a minute.